Bismillahirrahmanirrahim. So inshallah today we will continue our synchronous generator with measuring synchronous generator model parameter. So I really hope that last week you understand what we cover until the top in synchronous generator. So in order to measuring the synchronous generator models, so there are three quantities that to be determined. Okay, so the first one is the relationship. Okay, the relationship field current, and which is IF, and also the EA. So because IF is will provide the flux. Okay, so if you still remember, the EA equal to K flux omega. So IF will contribute to by increase of IF, the flux will be increased. So since flux and also generated voltage is proportional to the flux, so therefore we need to have the relationship. Okay, and then the synchronous reactance. Okay, so as we know previously, there's a there are two reactants. One is the what? There are two synchronous. What kind of synchronous reactance? What? Yeah, synchronous reactance equal to what? X and also XA. Okay, armature reaction and also a self-inductance. Okay, so combined together become the synchronous reactance, and also the armature reactance, armature resistance. Armature resistance. So there are three things okay, that we need to determine. So in order to determine these three things, so we need to conduct two kind of tests. So the first one is the open circuit test, and the second one is the short circuit test. Okay, so by doing the open circuit test, so the terminal of the generator is open circuit. Okay, so still remember the equivalent circuit. Okay, so we assume like this, and then this is a terminal, so this is open circuit. Okay, so this is EA. Okay, this is open circuit, and generator run at a rated speed. So there are inputs. Okay, so IF will be at the rated. Okay, we need to set. So then we increase slowly in step, and then terminal voltage is measured. So we'll measure this one, the terminal voltage. So they will produce a open circuit characteristic, okay, graph. So OCC. So by doing a open circuit test, the V phase will be equal to EA. Okay, because the current over here, current IA is equal to 0. There is no current because it's open circuit. So therefore V phase equal to EA. So then short circuit test. So terminal of the generator is short circuit. So this one will be short circuit through the ammeter. So we will put the ammeter over here. Okay, so we measure the IA or IL. So it's measured as a IF increase. So produce a short circuit graph. So there are two graphs. Okay, one is the OCC, and the second one is SCC. Okay, so this is important because sometimes maybe in the you don't know the parameter. Okay, you buy the things and you don't know the parameter. Okay, what you have is the data sheet, for example. So data sheet provide you these two graphs. So from these two graphs, you can measure the things. You can calculate the RA and also RA. Okay, so then yeah, since short circuit, in the short circuit test, so the short circuit test will be like this. Okay, so supposedly this y-axis actually is equal to EA. Okay, this is equal to EA. Okay, so since there is no current flow, so EA will become as a V phase. So as field current increase, so the V phase also will be increased. Okay, and IA will be 0 because open circuit. Okay, so there is a saturated curve. So this is like a magnetization curve. Okay, so this region, okay, so this is the region where unsaturated. Okay, so this is the saturated region. Okay, so yeah, this is due to the air gap. So at the beginning there is no ionization, and then once you increase the current, I feel, so the current will produce the magnetic field, so become the ion will be there, and then it will be become saturated. Okay, so in the short circuit test, the current will be linear. The graph will be linear. Okay, this is due to the short circuit. So the magnetic flux magnetic field is what we call is stator magnetic field. Okay, so stator magnetic field. Okay, for example like this. So B start, and also the B rotor is like a cancel each other. So the net is very small lah. Okay, the net is very small. So BR and B start is like a cancel each other. So then the graph will be become linear. Okay, so IA proportional to the IF. So still remember the equivalent circuit. So like this, and then this one RA, short circuit. So this is EA, this is JXS, and this is RA. Okay, current flow like this. This is IA. Okay, so the total impedance, so the impedance is Z. Okay, so in order to get the since this is the imaginary, you can see is in imaginary, so ZS equal to RA plus JXS. So this is including the phase. Okay, so to get the magnetic field, to get the magnitude, so we need to multiply with the conjugate and then become like this. Okay, so the conjugate is actually just multiple like this. RA minus JXS. If I'm not mistaken, like this. Okay, so then you will be they will become become like this. Okay. Okay, so yeah, since there will be ZS, so then like Ohm's law, so which is the EA IA ZS. Okay, so ZS is equal to EA minus divided by AEA minus divided by IA. So sometimes in the graph or in the question, so they give you some parameter, and then by looking at the graph, you will find some parameter. For example, they give you IF. Okay, so they give you IF. So for example, here is 2 ampere. Okay, so what is the VT? So by 2 ampere here, you need to look at the graph, and then do some like this, and then you will get the VT. For example, this is 10 volt, for example. Okay, so that is the importance of the graph. Okay, so normally the graph is given, is like a data sheet. Okay, so yeah, as we know previously, we normally do the assumption. So where we assume that XS, or the synchronous reactance, is more or significantly bigger or larger than RA. So we ignore the RA. So we can ignore RA. So the equation is become like this. Okay, XS. So which is ZS is equal to XS. Okay, it's equal to EA minus divided by EA divided by IA, or the open circuit. The open circuit. Okay, so since EA is equal to V phase, so it become you can put the open circuit value. Okay, and then become divided by IA. Okay, so however, please be reminded that not every question or not every problem you need to ignore the RA. Okay, it depend on the question or depend on the problem. Okay, so yeah, normally this is the practice. Okay, yeah. So sometimes even though sometimes you include the RA, so the result is slightly different. Not a very big difference, but a very slight. Okay, so for example 1.04, and then when you ignore, you will get a 1.02. So just 0.02 difference. Okay, so then we go to the example. So please look carefully. So for example, this question. So in this video also they will provide you the solution. So for example, 200 kilo volt ampere, 480 volt, 50 hertz, Y connected. So please be remember. So this is important. So you need to know which kind of connected, what type of connected. Okay, so Y connected synchronous generator with a rated field. So rated field current 5 ampere, and the following data were taken. So they buat test, so they do a test, and then this is what they get. Okay, this is the conclusion of the test. So they get it as a VT. So at the rated IF was measured to be 550. So VTOC equal to 540 volt. So and then IL, short circuit, at the rated IF was found to be 300. So IL SC is equal to 300. So what is the relation between the V phase and also the V terminal? So VT, what is the relation between VT and V phase? Who can answer for this Y connected? Anyone? Senyap ni semua. Okay, so for Y connected, so VT is equal to square Z3, okay, times with V phase, where the IL will be the same as a IA. Okay, so in this thing we can get already few parameter by know this. Okay, so and then they said when a DC voltage 10 volt was supplied to the two terminal, a current 25 ampere was measured. Okay, so since this is a Y connected, so we need to draw first. 1, 2, 3. So there is 3 RA. RA. Okay. So two point is connected with a 10 DC volt. Okay. So 10 volt. Okay. And then the current is 25 ampere. Okay. From here we can we calculate the RA? Can we calculate the RA?
Yes.
Okay. So by doing Ohm's law, so V equal to IR, so V is 10, I is 25, R is, since these two is in series, so they will be 2 RA. Okay, so then we will get the RA. Okay, so then we look at first. So find the value of the armature resistance. So armature resistance, so this is the how we measure. Okay, boleh siapa kira tak? So 50 10 bagi 1.5 0.2 ohm, 0.2 ohm. Okay, and the approximate synchronous reactance. So dia nak RA and also the synchronous reactance XS. Okay, they will be in generator model at the rated condition. Okay, so this is the solution as I draw before. So the RA become 0.2. Okay, so RA is equal to 0.2. So and then EA, so as we know before, the EA is equal to V phase, okay, and V phase is equal to, so VT equal to 3 V phase, so V phase become VT divided by 3, okay, and then we divide it, then we will get this one. So this is the EA, okay. So to get the ZS, okay, to get the ZS is equal to what? So there is RA plus XS square, okay, so then become, then XS we don't know, RA also we don't know, okay, and we have only this we don't have, okay, it's okay. So we have ZS equal to EA divided by IA. Am I right? Okay. So you can use this one as ZS. Okay, don't use this because the RA is there. So use this one. So EA is divided by IA. Okay, is equal to ZS. Okay. So since this is the Y connected, so IL is equal to IA, so become 300. Okay. So from the graph, so where is the graph? Alamak, tak ada graph lah kat sini. Okay, tak apa, it's okay. I think no need to see the graph. Okay, so we have the IA, we have the EA, we have the IA. So we can get the ZS. Okay. So we can get the ZS. Okay, so we can get the ZS, which is the EA divided by ni 8 volt divided by 300. Okay, so the answer will be 0.12. Okay, so this is the answer. Oh, this is so this is the ZS. Okay, so this is the ZS, and then once we get the ZS, we expand the equation, so including the RA and also the XS. Okay, so then we can get the XS. Okay. Okay, then the question just want to test, okay, the effect of RA. Okay, now try assume that the RA is 0. Okay, try assume the RA is 0, and then yes, from this ZS equal to EA IA, right? So and then so RA0, so then we can be test by using we can use this one, this equation. Okay, so actually we get the yeah, 311.8 divided by 300. Okay, so then we can get the 0.4. Okay, so 1.04 ohm. Okay, compared to the 1.02. okay, this is RA equal to 0, so RA equal to 0.2, there will be 1.02 ohm, so the XS. Okay, so you can compare, we can compare, so only slight difference, 0.2 ohm. Okay, so very small, the difference. Okay, okay, so then we draw everything. So once we get the parameter, we draw the complete circuit. Okay, so say that since the error in XS due to ignoring RA is more smaller than the error due to the saturation effect. Okay, so approximate calculation, normally we use this one. So we can use this one. Okay, so in the real life, so if in the test or in the theory, since whatever they give you RA, so we need to calculate. Okay, so in real life sometimes we can ignore because it's very small, not significant, not significant. Okay, so then the everything parameter, the complete circuit, we can redraw. We can draw the equivalent circuit. So by putting the RA and also the XS. Okay, and also the EA value. Okay, so this is how to answer this kind of question. Okay, so do you get it? Okay tak? ada tak kat sini? Ke dah tak ada ni?
Ada, Doktor.
Okay, so then kita buat next example. Okay, so we read first. So 480 volt, 60 hertz. Okay, so now we deal with the delta connected, delta type. Okay, 4 pole synchronous generator has the OCC. Okay, so now they give you the graph as shown in the figure below. So this generator has a synchronous reactance of 0.1. So since you can see here, they give you already. Okay, XS is known, and also RA also is known. Okay, so at full load, the machine supply 1200 ampere at 0.8 power factor lagging. Okay, so this is IA. Okay, and then under the full load condition, the friction and the windage losses are 40 kilowatts and the core losses are 30 kilowatts. Ignore the field circuit losses. Okay, so what is the speed of the generator? Okay, what is the formula for the speed? Generator speed, synchronous generator speed. What is the equation? And M equal to 120 FE divided by number of pole. Okay, so and then how much field current must be supplied to the generator to make the terminal voltage at no load. Okay, so they say like this, terminal voltage 480 at no load. Okay, 480 at no load. So we draw like this, we draw. They mentioned already, so this is V terminal, V terminal over here. So V terminal, since this is delta connected, so VT equal to V phase. Okay, so this is EA. So since there is no load, okay, so when there is no load, we can assume that there is a open circuit, okay, or IA equal to 0. Okay, so when there is no load, so mean there is no current, no current. When there is no current, so what we know is EA will be equal to V phase. Okay, so how much field current? So field current IF. So from here we can see so V phase is equal to 480 and then equivalent to the EA. Okay, so then we look at the graph, and then from the graph we can get the IF. Okay, so that's how we look the graph. Okay, and then if the generator is now connected to the load and the load draw 1200 ampere at 0.8 power factor lagging, how much field current will be required to keep the terminal voltage equal to 480? Okay, so I think better we try to solve one by one. So this is the graph. Okay, so this is the graph. We try to solve the one by one. So yeah, so since this is the delta connected, so V phase is equal to VT, so IL is equal to Z3 multiply with the I phase. Okay, so the question one is what is the frequency or the voltage, the motor and speed. So the motor speed, okay, so 120 times 60 divided by 4 poles will become 1800 RPM, revolution per minute. Okay, and then for the B, VT, as I said, IA is equal to 0, EA equal to V phase, therefore VT equal to V phase equal to EA equal to 480, and then from the open circuit, so open this, from the graph, so from here 180, and then we assume it will be in this range. Okay, so yeah, during the exam if this question come out, you can assume okay, so in the, but don't janganlah letakkan 4.1 kan, 4.1 macam tak kena sangat, so pandai-pandai lah macam ni nampak tengah, so we can see that this is quite in the middle, so you can put as 4.5 okay, so 4.5 ampere. Okay, so if the generator, so question 3, if the generator supply is 1200 ampere, then the armature current, this so this one you need to remember that this is not the IA but this IL line current. Okay, this is line current. So previously I think I said the IA, so I'm sorry, but this is line current. So we need to do some calculation. IA is equal to IL divided by Z3. Okay, so it's like this. Okay, I phase. So we need to OIA, and then we can get the IA. So, but the question is what? Okay, the question asks you if the generator connected to the load. Okay, so what is the field current? Okay, what is the field current to maintain at the 400 ni? Okay, so we need to look at the figure. We need to look, do the phasor diagram. So we need to calculate the phase. So this is cos theta, power factor is 0.8, so cos theta equal to, I think, negative 36. So negative is because of lagging, 36 point something. 36 from 87. Okay, lagging. Okay, so then we draw. So we just draw it first. Okay, so yeah, since there is AIA, so we just draw first. We draw this. Yeah, as we know that a V phase. Okay, so there is a V phase V phase is always 0, the reference, and then the IA. Okay, so this is IA times RA, and then 90 degree will become XS IA, and then we just combine, connected it. Okay, so yeah, I think from the previous equation also we know that the EA is equal to V phase plus RA IA plus JXS IA. Okay, so V phase they say is 480 volt. Okay, so the phase is 0 volt. Okay, so this is known, RA is known. Okay, IA is known, XX is known, IA is known, so we can get the EA. Okay, so then we put everything here. Okay, and then we will get the EA. So from this EA, the question asks the I field, right? Field current, right? The field current, right? So the field current. Okay, the field current. So once we get the EA, so we need to look at this graph, because this is open circuit. Okay, so please be remember that the reason why we want to look at the open circuit is because this is represent actually is EA. Okay, so since there is no current or the open circuit, so become equal to V phase. Okay, so but in this case, in this question, V phase is some value, and then the EA is another value. It's not a open circuit, but the graph is actually the relationship between the EA and also the I field. Okay, so then from here we can look at the graph. So 532. So we look at 532 is somewhere here. Okay, somewhere here. Maybe 5.7 for example maybe 4.7, 5.7. Okay, correctly. Okay, so somewhere like this Okay, so please remember that the OCC graph is actually the EA versus IF. Okay, so sometime because of open circuit, so there will be EA equal to V phase. So then we have a V phase, so V phase is equal to something and then equal to the EA. Okay, then we get the power. Okay, they ask the power. So what is the power? So just use the equation. Okay, so VT, VL. Okay. Okay, so I think just put everything. Just put everything here, and then we can get the P out. Okay, and then they ask for the input power. So input power, we know that the P out plus the power loss. Okay, so there is an electrical loss, mechanical loss, and P3 loss. Okay, so we calculate everything, so then we can get the answer about the P in. Okay, so then we can calculate the efficiency, so which is the P out divided by P in times 100. Okay, so in efficiency is in percentage. So then we can get the 95.7%. Okay. So then the next question, if the generator load was suddenly disconnected, okay, so dia tengah tiba-tiba dia disconnect, okay, so the current IA would drop to 0, okay, the IA drop to 0, so making EA equal to V phase, okay, dah become open circuit okay, bila dia disconnect maknanya dia open circuit, okay, so since the field current has not changed, okay, so field current is still the same, okay, so the magnitude has not changed, okay, and then the V phase and VT must rise, okay, to equal to magnitude, Okay, so they say that the magnitude since the field current, okay, so they say bila dia dah open circuit kan, so bila dah open circuit, so IA become 0, so then V phase equal to EA, and then since the field circuit saya beritahu ni. Okay, so I field kat sini, field current kat sini, so ni armature current, so ni become 0, so EA equal to V phase, okay. So bila dia cabut, dia disconnect, so V phase is equal to EA, and field current ni still running, okay, still running, IF still running, okay. So then the magnitude of EA has not changed, and V phase and VT must rise to equal to EA. So therefore, if the loaded will suddenly drop, the terminal voltage of the generator will rise to 532. Okay, so dia akan jadi balik yang tadi tu lah, yang macam kita kira tadi, EA tu. Okay, dia akan jadi balik EA lah, equal to EA. Okay, so soalan ni tanyalah, kalau dia cabut, kalau tengah run, okay, when there is running, and then suddenly we disconnect the circuit, disconnect the load, what will happen, and what will happen to the EA? So EA will go back to the become 532. Okay, so the V terminal will be rise. Okay, so sebab dia tengah loaded kan, so from 480, okay, so it's rated value kan. So tengah run 480, tiba-tiba je dia disconnect. So once they disconnect, so the EA will be increased, become 532 volt. Okay, so yeah, will be equal to EA. Okay, so you can see here that EA is much more bigger. EA bigger than V phase. This is due to the lagging loaded. So then if the generator were loaded down with 1200 ampere and 0.8 power factor leading, okay, tadi kita tengok lagging, so now leading, okay. So while the terminal voltage has 480, so terminal voltage tetap sama 480. So then the internal generator voltage would be apa pula? EA, okay. So V phase dah ada, so V phase ni V terminal, so V terminal equal to VT equal to 480. So EA is equal to what? Okay, so this is the calculation now. So IA, of course, it will be the same. Okay, 600 something. Okay, so we need to calculate by using the leading power factor. So no negative over here, no negative. Okay, no negative. Okay, so positive power factor, positive phase for positive angle. Okay, so EA will be 451. Okay, so you can see that EA is lesser then mana ada sama, okay, tak apa, it's okay, then V phase okay, EA is lesser than V phase. Okay, so this is 480 and this is 451. Okay, so the terminal generator voltage EA must be adjusted to provide 451. So to adjust the EA, we need to adjust the IF. Okay, so to adjust the IF, what is the IF, the suitable IF? So we need to refer back the OCC. Okay, OCC graph. So this is EA value. So if VT is remain to 480 according to OCC graph, so the field current will be 4.1. So 451 okay, katakanlah kita ambil dekat tengah-tengah ni ke kan, for example so kita katakan 4.0. okay, 4.0 atau 4.1 yang dia tulis. Okay, so acceptable lah. So kita akan ambil range lah. Okay, so nanti kita akan ambil range. Okay, so this is the answer. Okay, so far macam mana? Okay tak? Okay, now we continue to the synchronous generator operating alone. Okay, so sometime in TMB also they use parallel generator. Okay, so bila parallel generator tu, so dia akan jadi power lebih tinggi lah. Okay, and then most of the operating parallel, for example TMB use this, TMB power plant. Be also possible to operate alone as an emergency. Okay. However, sometimes assumption have been made. So they do a assumption. Okay. So for the assumption, the effect of RA is ignore. It's ignore, and then the speed generator will be assumed constant. Speed generator will be assumed constant, and then rotor flux also they assume constant. Okay, so this is how it look like. Okay, so and then increase in load. Okay, increasing in load will cause increasing in real power. Okay, and reactive power. Okay, so drawn from the generator. Okay, so the load current is increased. Okay, load current will be increased. Okay, so same goes to the other things. For example, you have a DC motor, and then once your motor is running, while your motor is running, try to put some burden, okay, for friction, or try to macam stop it. Okay, and then if you have the oscilloscope or something, you can see the current. Okay, you can see that the current is increased because of the load is increased. Okay, so once the load is increased, so the current will be increased. The voltage is still the same, but the current is increased. Okay, so then if IF, field current, and flux, and also angular velocity, and also the EA are constant, what does vary with the load changing? Okay, everything is constant. What is the thing that is changed? Okay, so the load is changed, and then what will be effect? Okay, the effect will be at which parameter? Is it the IF? IF is constant. Is it the flux? Flux is constant. Velocity is constant. Okay, so what will be changed? Okay, then we use the Phasor diagram with lagging unity and leading power factor, showing an increase of the load. Okay. Okay, so the blue one is the normal one. Okay, the red is the change in load. Okay, so the blue one is the normal, and then we increase the load. Okay, so once we increase the load, what will be increased? Okay, they say that IF is maintained, flux is maintained, omega is maintained, EA also constant, so become maintained. Okay, so once the load is increased, okay, so once the load is increased, the voltage will be dropped. Okay, so the voltage will be dropped. Okay, so V phase will be dropped. Okay, you can see here the voltage will be dropped, and then the IA, the current will be increased. As I said before, the current will be increased. So which current? So the armature current or the line current. Okay, so the current will be increased. Okay, but the EA will be constant. Okay, so the EA here is the same like this. So for example, this is like a bulatan, like a circle. So they're moving like that. Okay. So the current will be increased. Okay. Voltage will be dropped. Okay. So since IA increase, so the phasor diagram will be also become longer. However, the EA still maintain. Okay. So what kind of thing is changed here? So IA, V phase, and also the angle. This angle. Okay, this angle become increase. Okay. So by put the lagging, this is effect of lagging load. By increase the lagging load, so the inductive load, once we increase the inductive load, so which is the lagging, so the voltage will be dropped. Okay, the voltage at the terminal will be dropped. Okay, these three things will be increased, and then the voltage regulation will be positive. Okay, will become larger. Okay, so what happen when we increase the unity load? Okay, we increase the unity load. So actually there is a unity system, but we increase. For example, the IA and also IA have the unity power factor. So power factor is equal to 1. Okay, so which means that the previous one also the same power factor. Okay, this one also same, same power factor. So all of these cases is similar power factor, but the load is increased. Okay, so the effects once the increase in load of unity power factor. So same goes to the phase. Okay, voltage terminal or V phase. So V phase will be slightly drop. Okay, slightly drop. Okay, and the EA will be maintained. Okay, IA will be increased. Okay, so and also this angle will be increased. Okay, so this kind of three parameter will be increased. It will be changed. Okay, for the power factor of unity. Okay, so voltage will be dropped, but slightly drop. So and then the voltage regulation small, but positive value. Okay, but what happened when we increase the leading power factor? Okay, so the system is already leading, but we increase the leading power factor. Okay, so same power factor, but once we increase the load, so the current will be increased, the phase over here will be increased, EA maintain, so EA maintain, IA increase. So since EA is the phase here is larger. Okay, so in order to connect this point, okay, so we have already IA, so V phase become bigger. Okay, so V phase become bigger, okay, or larger. Okay, so compared to the others are reduced, and this one will be increased. Okay, and then how to correct the terminal voltage? Okay, in order to correct, so yeah, of course some kind of changing we need to overcome. Okay, yeah, this is theory by changing the power factor, but in real life, what of things that we need to change actually? Okay, how to correct the terminal voltage? Okay, so in order to correct the terminal voltage, okay, if you still remember the equivalent circuit, so like this, so there is a RF with variable resistor over here. Okay, and then this. Okay, So this is EA. Okay, so we need to change this RF. Okay, we need to adjust the IF, whether to increase or to reduce. Okay, so maybe we need to increase or maybe we need to reduce. Okay, it's depend. Okay, to the condition. Okay, so if the voltage increase, so we need to increase the EA. So in order to increase the EA, we need to increase the flux. So in order to increase the flux, we need to increase the IF. So in order to increase the IF, so we need to reduce the resistance. Okay, so IA here, the IF, so we need more. So once we need more here, so we need to reduce the resistance. Reduce the resistor. We need to reduce the resistance, so then IF will be increased. IF will be increased. Okay, so this is what I have said. Okay, so in general or in conclusion, so if lagging loads, okay, if we increase the lagging loads, and then V phase and VT will be decreased significantly. Okay, and the voltage regulation will be positive in the last value. Okay, so and then if unity power factor is loaded, okay, and then the change is slightly decreased the V phase. Okay, and the voltage regulator is positive but in small value. Okay, so then if leading loads, okay, are added, and then V phase and VT will be increased. Okay, so the voltage regulation will be in negative value. Okay, so this is a voltage regulation formula. Okay, either we use a V no load minus V full load divided by V full load, or EA minus V phase divided by V phase times by 100. Okay, so both can be used. So since V phase is increased, so then become negative. Okay, for the leading loads. Okay, now look at the examples, the other examples. Okay, so look carefully. So what kind of connected type dan sebagainya lah. Okay, so now we have a 480 volts, 50 hertz, Y connected. Okay, so I think the best once you look at Y of delta connected, terus you type kat sini. Okay, terus you type. Kalau Y connected, the IA or IL is equal to IA. Okay, so V equal to like this. So to type tu kat situ. So just directly type, so supaya you tak lupa lah. So 6-pole synchronous generator has a per phase synchronous reactance 1 ohm. So it is full load, amateur current is 60. Okay, kena ingat so full load at 60 IA. Oh, not IA, the IA equal to IL lah. Okay, and then power factor is 0.8 lagging. So this generator has a friction and losses, this value, and then 1 kilowatt and 60 hertz at full load. So since the amateur resistance is being ignored, so since amateur resistance being ignored, so means that RA is equal to 0. Okay, so of course once RA equal to 0, so losses also will be negligible. Okay, ignore lah, boleh ignore. So the field current has been adjusted so that the terminal voltage is 480 at no load. Okay, so 480 at no load. So this situation, okay, so this situation when at no load, so no load mean that IA equal to 0. So what happen when IA equal to 0? EA equal to V phase. Okay, or VT, okay, or V phase, okay. So the first question they ask about the speed rotation. Okay, so the second one is what is the terminal voltage? Okay, terminal voltage VT of the generator if the following are true. So kalau kita letak loaded, once we put the loaded 0.8, what is the VT? If rated current is unity power factor and then leading power factor, what is the VT? So then we need to calculate lah. Okay, and then they ask about the efficiency. Okay, to get the efficiency we need to have the power, the P in and also P out. Okay, so when operated at a rated current 0.8 power factor lagging, and then how much shaft must be torque must be applied. So torque apply, how much? Okay. Okay, and then what is the voltage regulation? What is the voltage regulation of the generator at 0.8 power factor lagging, and then at the unity power factor and also at the leading power factor. Okay, so the summarize first. Okay, so this generator is Y connected, so the phase voltage become so this value. Okay, so this is the equation to convert n. So and then that means that VT adjusted to 480. So V phase is 277 volt. So the field current IF as adjusted so that the VT 480, so that the V phase 277. So at no load the armature current is 0, as I said before. IA is 0, so that the armature reaction voltage drop are 0. So since IA is 0, so the EA equal to the V phase. And then yeah, so they say the internal, so this is the equation of the EA. So it varies only when the field current change. Okay, so since the problem state that the field current is adjusted initially and then left alone, so the magnitude of the internal generated voltage is EA. Okay, so mean that the EA is fixed and will not change in this example. Okay, so and then they ask about the speed. So this is equation about the speed. Okay, Fe is equal to Nm P divided by 120. So therefore, so we put everything and then we get the 1000 RPM. Okay, so this is the alternative okay, to get the angular velocity. Okay. Okay, so first of all that this phasor diagram is wrong because RA is 0. Okay, IA is 0, so they should be like this. Oh, lama tadi. Okay, kita assume je lah. Okay, okay, so ni tak ada. Okay, so IA tak ada. So ni value ni pun salah ni. Graf lain, saya silap kat sini. So if the generator is load down with the rated power factor lagging, so the resultant phasor diagram look like below. So V phase kita ada EA and then kita ada IA. Okay, so ini bukan open circuit lah because dia kata dah loaded. Okay, ada power factor kat sini loaded dengan power factor ni. So kita pun kalau nak mudah kita buat circuit lah, equivalent circuit tu. Okay, dia kata dia ada load kat sini. So kita ada XS. Okay, EA. Okay, so ni VT lah. Okay, V phase. Okay, so kalau kita buat voltage KVL Kirchhoff voltage law, so kita akan dapat VA equal to V phase plus JXS IA. Okay, RA tak ada, so IA tu boleh ignore. Okay, so dia tanya So current dah ada ke belum? Okay. So current dah ada because dia kata 60 kan, rated tadi, rated 60 volt. So kita just calculate power factor tu 0.8. So phase is equal to negative 37.8 lah. Okay. Ni lagging alamak 3 pula G. Okay. Lagging. Okay. So then V phase dah ada. So V phase they said 480 kan. 480. Okay. So kalau kita tengok dekat phasor diagram ni. So saya buat color lain So ini kita panjangkan. Dia jadi 3 segi kan. So jadi macam apa panggil? Macam ni lah rectangular. Okay, so ni 90 degree. So kita boleh gunakan teorem Pythagoras A, B, C. Okay, so C square equal to B square plus A square. Okay, kita boleh cari EA lah. So kita nak cari EA ni. Okay, so kalau kita guna ni dia mungkin susah sikit. Okay, tetapi guna ni dia lebih mudah. Okay. So V phase dah ada. And then this value magnitude ni dah ada dah ni. Ni magnitude dia ni. Okay. So XS ada. V phase ada. IA ada. Theta pun ada. So angle ni dah ada kan. Angle ni sama dengan angle kat sini. Okay. So sama dengan angle sini lah. Okay. So kalau kita buat sini EA, so dia sebenarnya nak panjang ni lah. So A ni adalah A is equal to V phase plus XSIA sin theta. So mana pula datang I theta ni kan? Mana pula datang bahagian ni kan? So ini bahagian bawah ni, nampak ni? Ni panjang yang bawah ni kan? So kita ambil yang ni. So yang bahagian sini adalah JXSIA. So kita nak yang sini kan. So saya tak hafal. Okay. Theta equal to X JXSIA. Okay. Ni saya tak hafal. Sin. Okay. So kita darabkan dia lah. So dia dapatlah bahagian sini. So magnitude lah. Ni kalau magnitude dia tak ada J lah. Kita ambil magnitude saja. Magnitude saja. Dia tak ambil kira J lah. Dia kira magnitude saja. Okay. So that's why they become because of this calculation ni teorem Pythagoras tu lah. Okay. Dia trigonometry. Kat sini dia panggil trigonometry. So teorem Pythagoras yang ni. Okay. So and then bahagian sini, sini nak juga panjang ni. Yang B ni kan, ni A adalah yang ni, B adalah XS IA cos theta. So kita tengok ni dah ada theta, so dia pakai cos pula. Kalau saya hafal. So cos theta equal to X, kita assume X lah and then become XSIA. So X equal to cos become XSIA IA cos theta. Okay, so kita dapatlah panjang ni, magnitude yang ni. Okay, so and then kita buat segi panjang semua. Dapatlah EA. So kita nak adalah EA. Okay, so then kita gunakan teorem Pythagoras. Kita dah ada A, kita dah ada B. So kita buat guna teorem Pythagoras lah. Okay, so C tu adalah EA lah. Okay, EA ni adalah yang B tadi, A square, yang ni B square. Okay, so then kita just masukkan nilai apa yang kita dah ada. Okay, we just put everything that we have and then we get the V phase equal to 236.8. Okay, so this is V phase. Okay, in order to get the VT, so we need to multiply with the Z3, then we get the 410 volt. Okay, so and then this is the same case. So they said that the power factor is 0, the power factor is 1. Unity power factor, so that just now 0.8 lagging, power factor lagging. So this is unity. Same case, same type of calculation. So since the power factor is 1, so just perfect triangle lah. Okay, kita dah ada 3 segi tepat ni kan. Okay, so and then dah tak perlulah nak pakai cos theta ke apa benda, tak perlu sebab dia tak ada angle. Okay, so you just use directly theorem Pythagoras, okay, to get the EA. Okay, so ni pun salah ni, gambar phasor diagram betul tapi value ni silap, value ni betul, silap saya. So value ni betul, value ni betul, ni 60 dan juga ni V phase lah. Okay, so kita ada EA, yang kita nak adalah V phase, so kita dapat V phase lah. Okay, kita dapat calculate dia punya VT terminal. Okay, so same goes to the power factor leading. Okay, so kalau leading macam mana pula nak kira? Okay, sama je. Okay, theorem Pythagoras, trigonometry. Okay, that is the tools. Okay, and then you need to draw first of all you need to draw the phasor diagram. So draw the phasor diagram and then try to do everything. Okay, and then you can design the trigonometry, and then trigonometry and also the theorem Pythagoras. So at this point we want to find these 3 triangle. Okay, only. Okay, so at this case, for example A, so A become V phase minus XS 1A sin theta. Okay, so dekat sini lah, ni A square, so this is the B square. Okay, so normally this point calculation is sama je lah macam sebelum tu, theorem Pythagoras yang sebelum ni kan. Okay, so sama yang ni kan. Okay, and then you will get the V phase. Okay, just put everything and then we get the V phase, and then we can calculate the VT. Okay, so in order to get the efficiency, we need to have the power. Okay, P out and also the P in. Okay, so in order to get the P in or P out, so at this case they use the V phase and also IA. So previously we look at the VT IL cos theta. So this is the same, the same concept. So since VT and IL, the connection is the connected type is different. For example, you want to use the Y type or delta type kan. So tak kisah. So V phase VT, so dia ada equation kan. So sometimes VT equal to V phase IL equal to this. Okay, so once you replace everything, you can get the same like this lah. Okay, so jangan terkejut lah kalau tengok tiba-tiba kenapa ni pula, kenapa yang ni, kenapa bukan yang ni. So you jangan salah faham lah. So dia adalah yang ni adalah yang asas. So bila dia replacekan yang ni, so dia akan dapat yang ni lah. Okay, so and then to get the P in, so we get the P out plus the losses. Okay, plus every losses, and then we get the 36.6 kilowatt. Okay, and then to get the efficiency, so P out divided by P in times 100. Okay, so then we get the 93.2%. Okay, in order to get the generator, the torque generator, the apply torque, so P in actually to get the P in or the apply torque, so it come from the P in. Okay, so apply, so we mean the prime mover, what is the torque that prime mover need to produce? Okay, the prime mover. Okay, so the prime mover need to apply the torque, so the apply torque and also the angular velocity will be become the P in. Okay, so now we just calculate what is the applied torque. So P in divided by angular velocity. Okay, so you will get 349.57 Newton meter torque. Okay, and then the induced counter torque is given by, so induced, so the induced, what is the induced torque from the converted before the output torque. Okay, so it's become the P converted. Okay, so if I'm not mistaken, the P torque, P converted is equal to the P out. Okay, so this is due to the ignore of some losses. Okay, I think because of there is no electric loss. Okay, so ignore the electric loss, so P converted become similar with the P out. Okay, so just use the P out value, okay, with the angular velocity, so we get the P converted. Okay, so if we can compare here, the applied torque will be more large. Is more than T induced, of course. Okay, so then this is the calculation of the voltage regulation. Okay, so where we already calculate the voltage. Okay, you can see here VT for the leading, and then 468 for unity, and 410 for leading. Okay, and the V terminal or the V no load still fixed, which is the 480. Okay, so we calculate 480 minus 410 divided by 410 times 100 become positive 17.1. And for the unity, just put it, and then we get a small. Still remember that we, in theory, that we say that it's positive but small value. Okay, for leading, okay, the V terminal will be more larger than the V terminal. Okay, or VT or V phase. Okay, so the value is negative. Okay, large negative. Okay, so in this example, the lagging load resulted in a drop terminal voltage. Unity power load caused little effect on the VT, and the leading load resulted in the increase in terminal voltage. Okay, so the increase, increase the terminal voltage. So this one slightly different, and this one is significantly reduced for the lagging. Okay, so this is the example 4. I encourage you to look at this video, and inshallah you understand more about the problem for the synchronous generator.